Thank you all so much for inviting me to give a talk at the IROS Multi-Agent Interaction and Relational Reasoning Workshop. My name is Kalisha Bullard. I actually just finished my postdoc at Facebook AI Research, and I am soon to begin as a research scientist at DeepMind. Today I'm going to discuss work primarily done during my postdoc at Facebook AI Research around multi-agent reinforcement learning for zero-shot emergent communication, and we'll unpack what that means. As a disclaimer, since I'll soon be starting as a research scientist at DeepMind as part of the multi-agent team, I'll likely be working on other projects within the multi-agent space. But today, I'm excited to share with you guys the exciting progress we've made on the problem of zero-shot communication and discuss the thoughts and feedback you may have. This is joint work with collaborators at FAIR. So multi-agent systems using technology are expected to become ubiquitous in society in the future. A diverse set of multi-agent systems is already beginning to be used in the real world. So you see some examples in the slides. A self-driving car in the top left, robots in a factory setting with humans in the top middle. Even traffic light system, which you may not think of as a multi-agent system, is several agents existing in a shared environment with decision-making capabilities that can work towards a common or conflicting goal. So these images show the heterogeneous nature of multi-agent systems, inherently including both multiple artificial agents and humans coexisting in the shared environments. My research broadly takes inspiration from these types of problem settings. So I really think a lot about cooperative multi-agent systems, and it comes from this idea that the world is inherently multi-agent, like the pictures of the biological multi-agent systems that you see. And I strongly believe that communication and coordination amongst AI agents and humans will become important and necessary if we're to move towards human AI coexistence when we think about these ubiquitous heterogeneous multi-agent systems in the future. There are many relevant application domains to multi-agent systems. I'm going to motivate this talk largely with the top two. So all of the four that you saw are ones that are interesting to me, but in particular, we'll think more about self-driving vehicles and robots in human environments as the motivating examples for this talk. So the first thing I want to do is motivate why multi-agent RL is a primary family of methods for the problem that we'll talk about today. Imagine that you have all of these embodied agents operating in a shared environment. And so the question becomes, if we believe that communication and coordination are necessary to get towards coexistence of the heterogeneous multi-agent systems, how can agents learn to communicate to aid in coordination? Now, you may think about supervised learning from data sets or imitation learning from demonstrations. But one challenge with supervised learning is that it would require huge existing data sets for each agent embodiment that you see. So for each car embodiment, you would need a data set, and you would also need one for each of the different communication skills you want the agents to learn. Multi-agent reinforcement learning, however, provides an opportunity to allow agents to learn a protocol solely through agent-agent interactions. So we can turn compute into data. Now, even when we talk about using multi-agent reinforcement learning as this powerful mechanism, there is this question of should agents have to train with every potential partner to infer a general communication protocol? And I think a key consideration with that is enabling agents to learn protocols that will generalize to unseen partners. So instead of having agents have to pair with every single car agent that they'll encounter, which seems to be intractable when you think about huge traffic systems, we want agents to be able to generalize, for example, to car agents that have not been previously encountered, but that they still need to signal to. So this work is motivated by this high-level research question of how can general communication skills emerge in embodied agents through physical action? And here are the two of the domains that we're using to motivate the work: self-driving cars and maybe robot arms that could be in some human setting. And so I will discuss these two papers, the work from these two papers as exploration of this question. So the learning problem is one of learning a communication protocol. And to give some background, so let's say you have a population of agents. Here we have a green, a blue, and an orange, 3 different agents. And a set of referents, which are really just communicative goals, something that we want the agents to be able to refer to. So let's call them communicative goals. The underlying idea is for each agent in the population to learn to generate messages for every communicative goal in the library that they've been given a priori. So the learning problem is for every agent to learn a policy mapping the set of communicative goals to the message space. A concrete example might be the goal is to greet and the message is wave. So referential games are really a type of multi-agent signaling game, which signaling games have been around for a long time. And referential games in particular have been used for protocol learning in the more recent literature. So the premise of the game is as such. You have a sender agent, let's call it Alice, that receives a communicative goal G as input. Alice generates a message M that Bob, the receiver, can observe. And Bob needs to make a prediction about what communicative goal Alice was trying to signal with her message. The loss or reward is looking at some similarity or distance between the intended communicative goal and the predicted communicative goal. Two important assumptions typically persist in this in the more general problem setting for referential games. One is that the communication channel is discrete, so the messages are individual actions selected from a set of discrete actions. And another is that it's a cheap talk setting, which means the cost of sending a message is zero. So this is a visual sample of prior work from the multi-agent communication literature in the deep learning era. So in the last, this is a more recent body of work in the last 5 years or so. And it's not intended, this sample is not intended to be exhaustive, but to briefly illustrate where prior literature has focused. The key limitation for embodied agents, though, are the two assumptions that we just talked about. So we're going to relax each of these assumptions one at a time, starting with the assumption of cheap talk. So the problem setting that we set this in our work is zero-shot coordination, which was introduced last year at ICML. This was actually work that came out of Facebook AI research. So it's a fully cooperative problem setting, and the zero-shot coordination setting is a setting where agents must learn to coordinate at test time with other agents who have been independently trained. So effectively novel partners, agents that they had no opportunity to interact with during training, but need to coordinate successfully at test time. And this work introduces equivalence mappings of policies, which are bijective mappings, and also formalizes the notion of symmetries for the underlying decentralized POM-DP. So I'm not going to talk in depth about that in this talk, but suffice it to say, or those concepts, but suffice it to say that we build upon these concepts in this talk, in our work. So in our work, we introduce and formalize the problem setting of zero-shot communication, which is an instance of the zero-shot coordination problem setting. The coordination goal is that agents must learn a communication protocol that effectively generalizes to unseen agents. So in the zero-shot coordination problem setting, typically agents will train in self-play. So here, this is a visualization of two different self-play agents, a green pair and a blue pair. So let's look at the green pair to understand the formalization. So in the communication game, you always have a sender and a receiver. Let's always call the sender Pi1. Pi1 gets some communicative goal G as input, and it can also make a private observation, O1. Then Pi1 can take an action A, which is generally going to be a communication action. The receiver Pi2 can observe the action taken by Pi1 and can also make its own private observation, O2, and then the loss or the reward is back propagated between receiver to sender. So in order to test for or evaluate zero-shot communication success, then effectively agents are swapped at test time. So agents engage in crossplay where every sender is paired with every receiver that it's never seen before, and vice versa. So here the green sender with the blue receiver, and vice versa. And what we want to assess is the agent's ability to communicate zero-shot with a novel partner. So you may say, well, that seems like a reasonable paradigm for training the agents. What's the problem with training using self-play? So one challenge is that when you train using self-play, you can have, what you end up with typically is many equivalent but incompatible joint policies or communication protocols. So in order to get successful coordination, what we need is for agents to agree on a protocol. And from an optimization perspective, what that means is we need individual sender-receiver pairs to converge on the same global optimum, the same joint policy or protocol. So let's say here's a high level simplified visualization of an optimization landscape. So let's say that each of these red dots represents a communication protocol that agent pairs can converge upon. And let's say one of these is an English protocol, one's a French protocol, and one's a German protocol. So now if you have two different sender-receiver pairs, there's no reason to believe a priori, they're training completely independently, there's no reason to believe a priori that they will converge on the same optimum or the same protocol. So let's say you have an English pair, so one converges on an English protocol and another pair converges on a German protocol, then we would not reasonably expect, if you paired the English sender with the German receiver at test time, that they would be able to communicate successfully because they've converged on different protocols. So what we want for zero-shot communication is to induce bias in the optimization landscape such that there's only one globally optimal protocol. So that way, even if you have sender-receiver pairs that are training independently of one another, they're all incentivized, given a sufficiently good optimization algorithm, to converge on the same globally optimal protocol. So now when you pair a German sender with a German receiver that it's never seen during training, we can still reasonably expect communication success at test time because the two converged on the same protocol. So our general approach for enabling this is twofold. The first thing we want to do is induce bias in the protocol learning with priors on the solution space. And we don't want to use just arbitrary priors. We want to use real world constraints to bias the solution space and engender a unique globally optimal communication protocol. However, we'll introduce some aspects that can make it such that even with the priors on the solution space, we still may not have a unique globally optimal protocol. So in this case, what we also want to do is adapt the learning objective to learn distribution over equivalent global optima. Or in general, what we want to do is this. So it would encompass the case where there's one global optimal protocol as well as if there are several. And we want to exploit equivalence classes of communication actions in order to do this. So this equivalence classes that were introduced in the zero-shot coordination work, we want to build upon that. So the first step, which is inducing priors from real-world settings. So, here again are the pictures of the high-level domains that we take inspiration from, and they exist in the physical world. So one bias that we want to take is that there's a cost to communicating using physical action, a cost in terms of physical energy exertion. So communication is no longer cheap, it's costly. The second thing is that in the real world, we would not expect all communicative goals to occur with the same frequency. So for example, we might expect yes or no to occur with higher frequency than turn right. So we induce a Zipfian distribution, which is a non-uniform distribution that's been used in quantitative linguistics in order to bias the weights or the frequency, the likelihood of the different communication goals. So when we put these two together, what this incentivizes is a minimal effort protocol. Communication goals that occur with the highest frequency should be mapped to actions that exert the least amount of energy or the least cost. So overall, agents would be incentivized to learn a protocol that minimizes the physical energy exertion or minimizes effort in communicating. Now, this picture that I'm showing you would suggest that given these priors from the real world, we should induce one globally optimal protocol. But what about when we have symmetries in realistic communication? So let's say you have the communicative goal, go ahead. So I want to tell a car that I see that it's its turn to go ahead. Let's say there are 3 different ways to do this that all use the same amount of energy. One is I can wave with my left hand saying, go ahead, it's your turn. Another is I can wave with my right hand saying, go ahead, or come on, it's your turn. Another is I can nod my head to say, you go. Now, if these all have the same amount of energy, then these are all 3 different communication protocols that exert the same amount of energy. So they're equivalent in terms of effort, but they're incompatible. So now I'm a receiver agent that trained with a sender that waved its hand to tell me to go ahead. But at test time, I see a sender agent that nods its head to tell me to go ahead. Then the problem is I'm going to have challenges interpreting the communication because our protocols are incompatible. How does this symmetry impact the optimization problem? Well, if there is no redundancy in the action space and no redundancy in the goal space, so every action has a distinct cost, every goal has a distinct likelihood, there is only one globally optimal way to map goals by likelihood and actions by cost. However, if we have redundancy in either one of those spaces, this basically leads to multimodality in the optimization landscape. So there are many different ways to have a minimal effort protocol. We're going to focus on action symmetry in this work. So actions that have the same cost or exert the same amount of energy for communicating goals, ambiguity in communication. So let's make this a little bit more concrete with one of our domains. So here is a discrete domain. This is visualizing two different sender-receiver pairs, an orange pair and a green pair. So I'm going to describe what this shows. In the left column, you have a visualization of the sender policy. The middle column is a visualization of the receiver policy. And the right column is a visualization of the confusion matrix that shows sender-receiver agreement. So starting with the right matrix, where we want to see probability masses along the diagonal, this is where the intended goal by the sender matches the predicted goal by the receiver. In the left column, the y-axis represents input given to the sender, which is the different communicative goals that it could have to convey. And then the x-axis represents output by the sender policy, which are the different actions that it can take to communicate those goals. In the middle column, the y-axis again is the input, but this time for the receiver. This represents all the different actions that it could observe the sender is taking. And the x-axis again is the output for that policy. For the receiver policy, it's the different goals it can predict that the sender is trying to communicate. Another thing that you see here is that's important to understand is if you look at the sender policies on the left, every single goal has a different likelihood, but the ranking tells you how likely it is. So goal 0 is the most likely a goal, then goal 1 next most likely, etc. And in terms of these blocks that you see, these E equals, these are energy classes. So basically ways of thinking about clusters of actions. So E equals 0 means that action 0 exerts an energy of 0. E equals 1 means all those actions 1 through 4 exert an energy of 1, and so on and so forth. So if you look at this, there's several different ways to get a minimal effort protocol. The 0th goal, communicative goal, should always be mapped to the action that exerts the least amount of energy, which is action 0. But goals 1 through 4 can be mapped to any of the actions 1 through 4 in any permutation, because all those actions exert the same amount of energy and you still get a minimal effort protocol. So these are two different ways to converge upon a minimal effort protocol, and there are more. And what we see here is that the agents are able to do really well with their training partners, and the diagonal tells us that in the confusion matrix in the right column. But now when we swap the agents at test time for cross-play, we see a huge degradation in performance. So from about 96% coordination success to about 45%. And on the right side in particular, that confusion matrix, you see that really the only thing they're able to get right reliably is intent 0 and mapping that to action 0. The other intents, they're not able to success. And intent 0 occurs about 44% of the time. So it says basically the best that they can do is predicting the most probable goal, the receiver predicting the most probable goal. So there's a question about how do we address this gap in communication efficacy between training partners and novel partners. So a baseline approach is to use self-play, and the self-play objective incentivizes each receiver agent pi2 to optimize for an individual sender, pi1 its training partner. So that would be like converging on only one of these protocols. But as we know, if your partner at test time converged on a different protocol, so a different red circle, then we have communication failure. Now, what we do is exploit this idea of equivalence mapping, so equivalence classes of protocols, and we use the other play learning objective for this. So what it does is incentivize each sender agent pi1 to optimize for an entire equivalence class of receivers, or vice versa. So optimizing for one's training partner, as well as any symmetry equivalent policies that the agent could presumably face at test time. And by doing this, it maximizes over not just individual policies, but equivalence classes over policies. Intuitively, what it's going to do is learn a distribution over these protocols, as opposed to putting all of its weight on only one protocol being the optimal one. So one question is, what does this other play objective optimize for in the referential game? So I'm not going to go into depth in terms of the objective function analysis, but what I will say is the objective function for a referential game that we typically use is going to be maximizing communication efficacy. So log probability that the pi is the joint policy, so it takes into account the combination of the sender and receiver policy. So the multi-agent system needs to predict the correct goal given the correct goal as input. So the sender policy would take in G as input. The receiver policy needs to be able to correctly predict G as the output, as the referred communicative goal. And then the other aspect of this, since we're in a costly channel setting, is that there's a cost for actions being taken. And so the derivation is in the archive paper, and so you're welcome to look at that offline. But effectively, there are two things that I want to highlight that the objective function is optimizing for. The first is trying to maximize mutual information between the communicative goals and the equivalence classes over actions. So given that an agent knows what communicative goal is being conveyed, it should be able to, with high probability, predict where in the action space should have high probability mass, or with high confidence predict where in the action space should have high probability mass. And given that an agent knows which action it's observing, then it should be able to, with very high probability, predict which goal is being communicated. So the mutual information creates a high correlation between goals and equivalence classes of actions. And the other aspect I highlight here is the minimizing the expectation in terms of the cost of the actions taken by the policies. So one question is, how can we obtain these equivalence mappings, these phi of A, because we want to create some link between the equivalence mappings of actions and the goals. How do we get those equivalence mappings? So intuitively, let's say we're going to play the referential game with this idea of symmetries. So now a goal is sampled from the environment, and agent takes action AJ in order to communicate this goal. So what we want to learn is a set of symmetries or equivalence mappings, capital Phi. So Phi IJ is just one mapping in that capital Phi. So let's say that mapping was sampled from the set. Then what it would do is transform AJ to AI, which effectively is an equivalent action that this mapping allows transformation to. And then the receiver agent would see that, make a prediction about the goal being communicated, and then the reward is back propagated. So what would happen is, if G prime is equal to G, the sender would learn that in order to communicate G, it should take action AJ. The receiver would learn if I see action AI, it means G. Now you can imagine later on in the game, in a different iteration of the game, that same goal is sampled. Now the sender takes a different action, a different symmetry or equivalence mapping is sampled from the set of equivalence mappings or symmetries, and the receiver sees something different. So now the sender updates its learning policy to say, not only can I take AJ to communicate goal G, I can take AI, which is what it's doing in this iteration. And the receiver learns, not only if I see AI does it mean goal G, but if I see AJ, it also means goal G, which is what it sees in this particular iteration. So basically compiling the information over several rounds of the game, the sender and receiver will learn these effective equivalence classes of actions. AI and AJ belong to the same equivalence class. So how does the algorithm do this intuitively on a high level? The other play algorithm that I introduced earlier assumes equivalence mappings or symmetries are given, and this is a limiting assumption in practice. So our algorithm introduces an iterative algorithm. It is an iterative algorithm which automatically discovers the symmetries. We initialize each equivalence mapping to an identity, and then for each iteration until convergence of the algorithm will train a new set of optimal zero-shot communication policies using the learning objective we derived, and then extract the symmetries from the behavior of the optimal policies. So intuitively, if let's say a receiver, let's say around a goal G needs to be communicated, two different sender agents choose two different actions or select two different actions to communicate that goal. So one selects action AI, another selects action AJ. The algorithm will infer this mapping that really is this transformation between these two actions that are presumably both different ways of communicating the same goal, because two different optimal senders selected these actions to communicate the same goal. And then the implication is that AI and AJ are symmetric actions, which means they can be used interchangeably to communicate goal G. And one nice thing here is that QED infers equivalence mappings from a learning perspective based upon the behavior of optimal agents, and it doesn't have to adhere to the formal mathematical definition of symmetry. So it can even infer quasi-equivalence, actions that are approximately equivalent that were based upon the behavior of optimal agents. So now, returning back to the same domain, we have the 5 intents, but each of them are now mapped to entire equivalence classes. So action 0 is in its own equivalence class. Intent 0 is still mapped to action 0 if you look at the sender policy. But actions 1 through 4, which all exert the same amount of energy, all belong to the same equivalence class. So intent 1 is mapped to a distribution over all these actions. So it can sample any actions 1 through 4 in order to convey intent 1. And then the receiver learns, if you look at the receiver policy, that if it sees any of the actions 1 through 4, all of them mean intent 1. And we still see high coordination success between sender and receiver. But now, now let's compare self-play and the QED algorithm for zero-shot communication success. Here we have 5 different sender-receiver pairs that have all learned minimal effort protocols, but that are equivalent but incompatible. And over on the right side, we have the QED algorithm, which learns a mapping between intents and entire equivalence classes of actions. So what we see is both are able to elicit good, strong performance with training partner, but there's a huge degradation in performance if we compare QED and self-play in terms of with a novel partner. And this is effectively because in the case of zero-shot coordination, each of these agent pairs has converged on the same protocol. So even if I've never seen you, I can communicate successfully with you at test time because we learned the same protocol. One trade-off here is that there's a higher energy cost associated with QED because it learns probability mass over the entire action space, including more costly actions. But we get increased performance by about 60%. So what about the continuous channel settings? So when we have an embodied set of agents, so now our sender policy is a robot arm, let's say, and the messages are motion trajectories. And this is underexplored in the multi-agent communication literature, but the message space really becomes intractably large. And so the question is zero-shot communication still possible in this continuous setting? We use a slightly different training method because this is ongoing work and we still haven't figured out how to infer symmetries in the continuous channel setting. So here we still do self-play for the initial protocol training. That's what these all mean. The circle with it's just like a sender-receiver pair. But now in order to train for zero-shot communication, we freeze the sender agents into a training set and a test set. Then we initialize and train new receiver agents, and each one of them will be trained as a best response to the entire set of training senders and then tested against the test senders for zero-shot communication success. So we do some qualitative analysis on a more simple task. So here we have only 2 communicative intents, 1 and 2. 1 occurs with the highest frequency. If you look at this diagram, time in training is going from the top to the bottom is over the course of training, and the x-axis is the energy exertion. So what we expect to see is intent 1 should be to the left of intent 2 because it should use less energy over the entire course of training, and that's what we see. The Gaussian at the right shows you the distribution over the energy values at the end of training for these 2 intents. And what we see is that these Gaussians are basically not overlapping. So there's very high mutual information between the goals and the cost or energy exertion for the action taken to communicate these goals. So if I were just to tell you what the energy exertion was and I didn't tell you which goal is being communicated, with very high confidence, you could predict just based upon energy exertion, never seeing the trajectory at all, which of the two goals is being communicated, the blue or the orange. And if I only told you which goal is being communicated, the blue or the orange, with high confidence you can predict what's the spectrum of energy values. Also, another thing to note is that the Gaussians are pushed all the way to the left. If they were moved further to the right, they would be high mutual information because there's little overlap, but they would be exerting a lot of energy. Pushed all the way to the left means they're also trying to minimize the energy exertion. And here's a visualization of trajectories. Some open challenges are that with these high dimensional trajectories as messages, it's difficult to actually pick up on this latent cost feature or energy feature. Performance degrades as the number of communication goals increases, and that's really because it's a combinatorial optimization problem. You're trying to correctly order communication goals, and the more of them you have, the harder it is to solve that optimization problem. And then discovery of the actual symmetries. Remember, the symmetries are not given, they have to be discovered. For continuous channels is still an open question. But it is promising in that we see zero-shot coordination is possible in principle, even for these continuous action protocols. So the motivating goal is emergence of protocols for embodied agents. The novel challenges that we had, these costly channels that derive from energy exertion and continuous channels. And what we contributed here was formally introducing the zero-shot communication problem setting, incorporating realistic priors to induce bias, a method for learning equivalence classes over actions, or just over policies more generally, and exploring optimization of continuous action protocols. And future directions really are thinking of still, pushing the boundaries in terms of inferring optimal zero-shot protocols. So how do we guide the policy search to more robustly converge on a global optimum? So even though we induce bias to have one globally optimal protocol, how do we reach that through our optimization algorithm? How do we discover and exploit symmetries in the continuous channel setting? And how do we automatically discover the cost-based latent structure for the continuous channel setting? And then also learning human compatible protocols. The work that I talked about here, or as you saw in the trajectories, the communication protocols look, or the communication messages look arbitrary, which is a key challenge in emergent communication because there's nothing to make them more similar to human expectations. So how do we actually align the communication protocol with humans to make it more compatible with humans? And this is joint work with collaborators at FAIR. So I want to, thank and acknowledge my collaborators. And with that, I'm happy to take questions.